All right, so today's topic is matrix manipulation using the Numpy package. If you recall a few meetings ago, and that was so last week, we did matrices as list. And there's like the cool matrix GIF. We messed with rectangular numbers. In building a matrix, we just defined it and then we manipulated it. But we had the added bonus feature during the manipulations that we had to deal with stuff index by index. Numpy, among other things, simplifies that from our perspective as live human beings that have to do this stuff and then move on to our next endeavor, such as binge watching bad television and so forth. So Numpy is a package that in addition to matrix manipulation actually confers some other useful stuff. So today we'll learn a little bit about NumPy, some array methods, and examples of using NumPy to illustrate its abstraction to making maintainable scripts. Because it's not too hard to realize back from lesson 8 that stuff maintained as a list was essentially unmaintainable. You get to some point, you won't be able to figure out what it's doing to fix it or repair it or make it scale. NumPy simplifies that by putting all that into the software, and that way you have something to blame. So reading from the mighty internet, it's the core library for scientific computing in Python. It provides high performance, blah, 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 BS, 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 marketing. The library's name is for numerical Python or numeric Python. And if you don't want to actually read anything about it, but need to know some of the bits and pieces, you can go to this lovely little, I don't like it being called a cheat sheet, because that's implying that somehow cheating is a good thing, which it's not. It's just a quick reference sheet. It's probably a better name for it, but whoever wrote the code that created it thought that quick reference was far too many characters as compared to cheat. Although technically it's not cheating if you know how to do it, you're just using this to help you remind. So that can be a philosophical argument that we can have collectively for the remainder of the semester. You'll never convince me it's a good name. There's got to be something better. I mean, the English language is like, it's like that thick in one of those little teeny dictionaries that you can barely see the print. So there's got to be a word in there that applies. Anyway, back to NumPy. One of the main data abstractions or structures in NumPy are arrays. One-dimensional arrays, we call them vectors because a guy named Victor was the first one to use it in the movie Airplane, and since that time it's never left us. Two-dimensional arrays are rows and columns, and when we get to n-dimensional arrays higher than 1, there's also this concept of axis. And so axis 0 in a 2D array corresponds to the row. Axis 1 corresponds to the column. We can go to 3D arrays. You can think of the third dimension as providing layers. So layers of two-dimensional arrays. So axis 0 identifies the layer. Axis 1 identifies the row in that layer. Axis 2 identifies the column in that layer. L-A-Y-E-R, not L-A-I-R, like critters waiting in to bite you. Although that would be a cool visual sight gag if I knew how to do that. That'll be for a future semester. I'll have a layer come out and get you. So there's two fundamental conceptualizations. First is data representation as arrays. And interestingly enough, it uses the array package internally all by itself, no help. And then the second conceptualization are various operations on those arrays. So there's element by element arithmetic, and there are certain mathematical operations. There's also vector matrix arithmetic, indexing, selection, copying, probably a bunch more. The main computational thinking concepts embedded in NumPy. So this appears from time to time throughout the lessons because we were told it had to be there. Are decomposition, abstraction, and algorithms. Okay, moving on to something useful. How you set up the module. In principle, or ideally. Whenever you hear a professor or someone pretending to be a professor say ideally or in principle, that's just code word for maybe you'll be able to get it to work, but if not, you're on your own. So in your Anaconda installs, you should be able to simply type import NumPy and import the package. That should work. If you do get an error, then you have to go through the whole sudo path to where you want to put it, pip install NumPy, or I would start with conda first, conda install NumPy, and then follow the instructions. And then after that doesn't work, go out to the mighty internet and find some instructions that do work. Here are a few links to things that are supposed to help. I get a little nervous when the URL has read the docs, you idiot, in the actual URL name. But these describe to some extent how to install. The Conda installer, as you'll recall, is accessed using the Conda PowerShell prompt, which I can't replicate here because I don't have a South American snake installed on my computer right now. It's usually in the upper left-hand corner. It's green with a little circly doodly boppy thing, and it will produce something that looks like that. And then you type the command lines into the PowerShell prompt. So we're going to assume it works for you because I've got no choice. So going back to NumPy, it's a very important library in scientific computing. So you'll probably use it, well, you certainly use it throughout this class, but you may use it later on in your fascinating engineering education career for pretty much doing computational linear algebra, because it's a lot. It doesn't perform any tasks that you could not program yourself. However, it can do in 1 or 2 lines of code, which might things that might take you 15 or 20 to accomplish the same thing. And if you accept the construct that every line of code that you type and attempt to run is a chance to make a monumental mistake. So 2 lines, that's only 2 chances. If you do 20, that's a lot more chances. So let's start with our friend, the mighty array. So a NumPy array is simply a grid of values as depicted here in the picture. Hence I use the word depicted, so I didn't have to tell you it was a picture because by definition it had to be. And it's indexed by a tuple of non-negative integers. The number of dimensions is the rank of the array, and the shape of the array is a tuple of integers giving the size of the array along each axis or each dimension. So here's a one-dimensional array, that's the top one, and the name of it is 1D array. Now, is that a valid Python name according to the naming conventions? That'd be a no because it's starting off with a numeral, but just pretend there's an underscore in front of it that you can't see. And it's indexed starting from the left. The first position is 0 and counting upward from that. So for example, the contents of the 1D array at index position number 2 is 7. You don't need glasses yet. 2-dimensional arrays, we have a row and a column indexing. The visual picture is the rows are counting down and the columns are counting left to right. And the ordering of the tuple of indexing is row column. So for instance, same kind of game, but different person has to answer. One of the blind people in the back, because I know you sit in the back because you can't see, plus it makes you further away from me, so my annoying voice doesn't wreck your afternoon nap. For example, 2D array, row 1, index position row 1, the row index 1, column index 2. What number the number bet's at? 12, right. Not your chronological, but your mental age for most of us in here. So the array itself contains information about the actual data itself, as well as how to locate an element and how to interpret or take information out of an element. To make a NumPy array, you simply use numpy.array function. So here we have a little a typist error, because np.array won't do anything based on that import. But if I aliased it to MP, which is what you'll see when you appropriate usable code off of the mighty internet for your own purposes, they'll probably do import numpy as np and then continue. You can just use the array function to create it. All you need to do is pass a list into it. So the initial creation of the array, there's no great advantage to NumPy because it's doing the same amount of work initially. But once the arrays exist, it has a lot of methods attached to it, which simplifies work. And if for any reason you actually want to read more about the differences between an ordinary old Python list and NumPy array, here's a wonderful link to University of Central Florida. So this is what their 4 students have to take in the equivalent of this class. Theirs even better because they got cool pictures. Whenever you see something like that, that immediately to me looks like somewhat useless documentation. But somewhere in there, there's probably a little bit or a gem of knowledge. Let's go and create a few of these for ourselves. I believe it's making me log on. Stupid. Ah, that's why. I guess I'll get out of the exam. All right. Oh, and I killed all the untitles. So let's take this one. Not that one. We don't want that one. That's a good untitled. So how do I get a new terminal window? Never occurred to any of you. Well, if you have a need to get a new terminal window, go into the file, pull down menu, choose new launcher, and you get these choices, and then click on your favorite picture. In our case, we're going to click on the terminal picture. And there was no reason to do that. I wanted a notebook. You didn't stop me. You just let me blithely go on. So in my case, I have to choose what kernel I want to use. Anybody have a preference? We're not going to use R. It's a different language. Okay, we'll use Python 3, which should be the same as on the actual operating system. So we have an untitled number 1. And if we run that cell, absolutely nothing happens as anticipated. So I'm just going to copy, paste, and run stuff initially. So we're going to import the NumPy package. Hopefully I don't get an error. Then we're going to create a list in the usual fashion. And then we're going to have it regurgitate back to us what kind of data structure that list is. And we shockingly get the no module named NumPy. Ah, hate it when that happens. B, new launcher. Python 38 kernel. It tells us that we have a list. Okay, no great startling revelation there. Let's explore that list a little bit. We'll go ahead and print it. And it prints the list back, and the key things I want to point your eyes out to: square brackets are enclosing this sequence of numerical values. That tells us it's a list, and each value is separated by a comma. We will now convert that list into a NumPy array. almost nothing is going to change, except now the data structure type has changed from list to numpy.nd array. ND means n-dimensional array. In this case, n happens to be 1 or 0, however it counts. And now that we have my list as an array, if we print it, lo and behold, it now prints the sequence of numbers without commas separating them. So that's it. That's the most awesome thing that NumPy does, is it deletes commas. There's a bit more to that. Let's make a two-dimensional array. Let's make a two-dimensional array. So I'm just copying and pasting from the instructor notes. Two-dimensional array starts out life as a list. And that's not good enough for it. But now when we print it, watch what happens. Piece of crap, computer. It's doing that thing again where it doesn't take input, it just does what the hell it wants. It's these 10-year-old computers will do that. Okay, so now we have printed our list, and in the outer list, how many objects are contained? 3 objects. What are those 3 objects? Each one of them is a list in and of itself. So there's the 0 object, which is list 1, 2, 3. There's the 1 object, which is list 4, 5, 6. And the 2 objects, which is list 7, 8, 9. We already know how to deal with that if we need to. But let's turn it into a NumPy array, and then we will print the contents of it. I think this will work, so I'll save time. I already know it's going to come out as a NumPy array, so we'll just go ahead and issue the print structure. All of a sudden, by use of NumPy, it prints it row-wise. We didn't have to do any shenanigans with getting the length of the outer list from its first dimension and the length of the inner list from its first dimension, and then doing that print by row IJ stuff. So that's handled for us in the mighty NumPyness. We can get the length of the list if we invoke the length in that fashion. By default, it always goes to axis 0, which in this case is going to be the row count. Or we can explicitly choose axis 0. Or we can actually get the shape of the list. If we were to put a 1 right there, and we get the length, we'd also get a 3 back because this thing has 3 columns. The shape is handy because it'll tell us that it's a 3 by 3 object. Now we'll create another list. We'll give it the cryptic name, my other list. I think that almost looks like mother list. And what my other list is going to be a collection of lists, each of them containing 2 things. So 2000, 2001, 2002, 2003, and so on. Then we'll print it as its core Python, and then we will print it again after we get its shape from NumPy, and then we will print it as a NumPy array. So we're just going to look at the same thing in several different ways. So the first thing it does when we use the shape function is it tells us there's 5 rows and 2 columns, and then when we print it as a NumPy array, it indeed expresses the list row-wise as it's designed to do. Next is array arithmetic. If you recall, back in lesson 8, if we wanted to multiply each element of an array by a vector, so here's our vector, we would read in our scalar and then we would get the length of the vector and increment through it one at a time, placing into a position the product of scalar and whatever was already in that position. Alternatively, we can do that in NumPy quite a bit easier. So let me copy that over and run it. So there's nothing new in this one. We did this in lesson 8. I'll scale it by the number 1 because I know that it's what it should be. And now we will accomplish the exact same task in the world of numpiness. Notice somewhat of an economy of coding right there. So oh, that's not the whole thing. Let me also get the so if I take that same list and convert it to a NumPy array, I could have actually just done array 1 as NumPy array vector. A single line accomplishes the same as these 2 lines. Well, 2 lines is only twice as many as 1, but half as many as 4. There's a lot of logic built into that part of the for loop that's easy for us to bugger up. And in this case, we don't have to worry about it. It just takes care of it. So that's pretty cool. We can also do element by element, raising things to power. So here's an example of printing the array. Everything's raised to the power 2. So this is how you take a circle and make it a square. So these are all squared. You got to do that if you want to put square things into round holes. Or we can use the power method. These accomplish the same thing. This one down here is probably more C++, and that's actually what's happening inside. I think at this point, whatever you prefer, as long as it works correctly, is more than adequate. We have the ability to find element of the array named Max. It's a little guy. He's where the wild things are. So it can find the maximum value in the array, and then we also can find the position of the maximum value of the array. So let's say we had to do that manually. So we have vector, and we want to find the position of the biggest thing in vector. So how do you do that in core Python? Well, I'll go ahead and just type some script here because it's always a good thing. Just start typing and hope for the best. Okay, so I've just declared big a very large negative number, which is anti-big. I don't have anti-big as an object. And now for I in range length what am I going to do? I'm going to if vector is bigger than big, colon. Don't need to do colonoscopies here. Colonic, yeah. So if a particular element of vector is bigger than big, what do I want to do? You have no idea what I want to do. You're just going to let me do it, right? Well, if it's bigger than big, then you make it equal to big and you move on. So big equals vector. else. That's not true. Just keep on going. And assuming this gets done, oops, need to keep track of something. Okay, so we have index and big, and when we get done, let's print index. Okay, it should come up as an 8. There's 9 elements in that array. The biggest one is all the way to the right, and it starts counting at 0, so it should identify the 96 and report back an 8, or a pink screen of I did it wrong. All right, that's what it took to do it in core Python. I used nothing up there that is not in the core Python kernel. We didn't use any array special, nothing special. That is as non-special as you can get. That's also, for all practical purposes, unmaintainable. 2 weeks from now, if I show you that script again without prompting your memory, you'll have no idea what the hell it's supposed to do. You're not stupid. You'll probably be able to figure it out, but at first glance, like, I don't know what this does. Whereas if we take, go ahead and pull the script over here. I want to find just one thing, dude. I think this will work. Hopefully it knows to convert that into, so either pink screen of you did it wrong, or so it got the correct element. And let's test our script. I'm going to leave it where there is only one big thing. So now I've moved the 96th from position 8 to 0, 1, 2, 0, 1, 2, 3 to 4. So if I run it by hand, indeed we get the 4 back. Run it using the argmax function. Clearly, that second one is a whole lot easier to maintain than this up here. One more fun trick and then we'll move on. So my home built stuff only reports the last one that it sees. So it reports the 9, whereas the NumPy one, I think, reports the first one it sees. It does. And there's probably a switch in the NumPy that you get to report all the ones that it encounters. So when there's multiple big values, they're not an identical algorithm, but you get the idea, or maybe you don't. We also have minimum. We can add and subtract arrays just like we did in core Python, simply by telling the machine that it's a NumPy array and then using add or subtract notation. Let me go ahead and get the same array that's in the examples, and we'll do that. You know, there's nothing to see here. Ignore the man behind the curtain. Okay, so there's my second array. Copy that. So now we'll redefine the 2 arrays, and we can add them and then subtract them. Okay, so the first one we'll take array 1 and add it to array 2 element by element. So ordinary matrix addition. The second one will take array 1 and subtract array 2 from it. And it, as displayed up there, it doesn't put them anywhere. So it's simply going to display them into the standard input output without damaging the original arrays. And sure enough, it did that. And to do the same thing back in the olden days when dinosaurs roamed the earth. Bless you. There's what it took us to add two arrays. So we had a nested for loop, and we had to create a destination for it. We didn't have to. We can, if we're willing to destroy one of the two arrays, we can do it in place. So again, the NumPy gives us some economies of scripting. We can multiply arrays in a variety of ways. Let's just do the dot product that we're accustomed to. So if we do this outer product on a 2 by 2, it produces the same result as the dot product. It's not very cool. I guess it's cool, but it's not of much use. So the syntax for multiplying one array by another using the inner product is the first array with the dot method, and then the second array that you want to perform the product with. And so we're going to declare multi-array 1 is equal to array 1 inner product with array 2. Remember what matrix inner product is. Takes the row of the first matrix, multiplies that element by element, column of the second matrix, adds the result, goes in the upper left-hand corner. Row of the first matrix, second column of the second matrix, that dot product goes in the upper right-hand corner, and so on. So this will produce a, let's see, 1, 2, this should produce a 4 by 4 output. Oh, it does none of the above. That's not correct. I broke something somewhere along the way. Redefine the matrices. That's bizarre. It's not functioning as I expect it to. If we do the same with ordinary lists, I got something defined wrong. Array 1 plus array 2. Oh well, I'll go back to my notes because I trust them. If we were to do that the old-fashioned way, this is what it would take to multiply the two matrices. And now we have a triple nested loop structure. We have an outer loop for rows, a first inner loop for columns, and a second inner loop for the row column transposing that's going on. So there's considerable savings in code crafting using NumPy. I'm still very baffled why that doesn't work right. Stop my kernel. Find the two arrays. Aha. Mr. Sanders got confused. It is being incredibly disobedient all of a sudden. There we go. That's better. Now we'll get back here and hopefully everything will be. Okay, that's as expected. That's still broken. There's something wrong with my kernel. Colonel Sanders had too much chicken before class today. It should produce this output. Now you have you all as learning this don't have the advantage of being able to look at output and know that it's wrong. You'll have to. So what part of the computational thinking problem solving protocol do we use to help detect things like that? If you are going to make a script and you can't tell if the machine's doing it correct or not, what do you do to be able to know if it's doing it correctly or not? You make your own simple problem to which you know the answer and feed that to your algorithm and you should get the same answer. If not, one of you two is wrong. Most likely in that instance, it's the machine. Some other functions in NumPy are the arange function, linspace. You'll probably use linspace later on this semester. And they have a function called zeros. Any guess what that does? Makes zeros. How about ones?
Just puts ones.
Right. How about twos? I don't think there is a twos.
Yes.
But there's even better than twos. You have random, which will produce random integers. We have the minimum function, max argument, arguments, reshape. So you can change the shape of an array. So you can change a 2x3 to a 3x2, or a 2x3 into a 6x1, or a 2x3 into a 1x6. All sorts of things messing it around, which will maximize your chances of taking a problem that you might have been able to solve and monumentally screwing it up. So keep that in mind. If you can't do it fast enough on your own, the computer can do it just as fast. We also have some mathematical functions that are conferred with the NumPy package, which are square root, exp, exponential, sine, cosines, log, natural log, and log 10. I don't think there's a log 11. Although there is a way to do a base 11 logarithm, but that's kind of this point just a novelty. Lastly, there is conditional selection. So you can select elements from an array based on conditional operators. So every element that's bigger than 3, you can pull out of the array. Every element that's between 3 and 9, you can pull out of the array, and so forth. And then we can use the copy function. And this seems like as much so what as you can imagine. But generally, when you're doing this for real, the arrays are going to be bigger than 2 by 2. You're not going to want to destroy your original input. So you create a copy, you do everything on the copy. It would be what you could do if you could copy yourself, right? You would create a copy and then try all the tattoos on the copy and see if it looks good or not. And if it doesn't, you can just delete the copy. It hurts a little bit, but you get over it and build another copy and keep going. There's linear algebra functions. If you recall, our matrices, even though I don't trust my kernel right now, Colonel Sanders, you fool. So we'll create two matrices, A matrix and B matrix, and we will test the conjecture. If they are inverses of each other, they should be, because I'm lazy, so I cut and paste from an earlier lesson. And we will see, we can use the inversion that's built into NumPy, linear algebra inversion of the B matrix, and see if we get A back. All right, based on my notes, this should be, oh, sweet, that worked. Okay, so that first collection, the 1, 0, 0, 1, what kind of matrix is that? It had a special name. Same thing immigration asks when you try to get into the country at the airport. But is your close identity? Yeah.
Okay.
It's the identity matrix.
Is it the 1, 0, 0, 1?
Can't see? I can fix that.
Oh,
Let's
it is
see.
one. Oh, yeah, no, that's.
Can you see it now? Huh? Can you see it now?
Come on.
Okay, and then the next one, we took the B matrix. We used the inversion function, which will invert a matrix, and we should get the A matrix back, which sure enough we do. Okay, so my smart ass response, let me get it back to normal size. Oh, that was on the recording too. Well, don't rat me out yet. You want to get to the end of the semester before you have to get a new professor assigned mid-semester. All right, continuing in 4 minutes or less. We can compare arrays. We don't have the same Boolean operators that we're accustomed to. So in NumPy, we use the equal operator or the greater equal. There'll be a less equal, and we can find out if element by element arrays are the same or different. And we can go to multidimensional array comparisons, and this does, again, element by element comparisons. So if you have two arrays, A and B, and you want to know if they're equal, if they're identically equal, you can use the comparison function. And if all the returns come back as true, then yeah, they're identically equal. If any return comes back as false, then they're not identically equal. And that may have consequences in the rest of whatever. It's not a useless novelty. Copy and delete are probably really useful. So if I was doing this on homework of any consequence, maybe not this particular homework because it's pretty simple. As soon as I get the array read in, I'd immediately make a copy. I'd do everything on the copy until I trust it. And then you have a delete function, which you can delete rows or columns. So let's look at an example. So here's an array called X, chosen because it marks the spot. And not much of an array. It's 1, 2, 3, which I selected because it's easy as ABC. I reversed it. It's a palindrome. Now we're going to assign Y so that Y is equal to X. And then we'll print Y. Sure enough, Y appears to be 1, 2, 3. Important safety note here. Y may not be a different object. It may actually be the same thing. It may be doing equivalence. But now let's make a copy of X and we'll call it Z, because I always use X, Y, Z because it's engineering class and all those books with arrows and vectors and so forth do that. So now we have 3 objects. One is named X. It's a list 1, 2, 3. Another one's named Y. It's also a list 1, 2, 3. It might be the same list. A third one is named Z. It's a list containing 1, 2, 3. And let's see if they're identical. Not with testing, just printing. So we will print 3. We have X equals 1, 2, 3, Y equals 1, 2, 3, and Z equals 1, 2, 3. Wow, big deal. Now we're going to change a value in the X matrix. We're going to make the first element a 100 instead of a 1, and then we will print the 3 things back. So before you see that, unless you're already looking at the answer, what do you expect the first print function to produce? You don't expect it to produce anything. You're all thinking it's time to go so we can do lab online and log in and then turn off our video and pretend we're actually there. I'm not going to let you go until you answer the question. 100, 2, and 3, right? Okay, what do you expect the print Y to do, the next line? Okay, that's what I was looking for you to say. Let's see what really happens. Interesting. Y magically picked up the 100. You ask yourself, why is that? That's because in that assignment statement, it performs something called equivalence. So this is the worstest thing about all modern programming languages, especially this one, is it does crap like that without telling you. Because like you all, I would have thought that y is a different object. So when we did the copy, that actually created a brand new object. And we can even explore that just a bit further and get the hexadecimal addresses of the three objects. So we're going to print the first address of X, the first address of Y, and the first address of Z. Let's press the keyboards correctly. And notice the X and Y object hex addresses. Yeah, I'll zoom those in for those of you that are blind. Anything odd about them?
They're all the same.
Yeah, the first two are identical. They are the same object. They just happen to have a different name. The third one is a separate object. So as you're doing stuff and you know you coded it right, and among other things, it doesn't make sense, or objects are changing without you explicitly doing it, keep this in mind. Sometimes assignment creates a brand new object. Other times it simply gives a second name to the same object. That is my personal opinion. That's a monumental flaw with this particular scripting language, but apparently Amazon likes it, so we're going to have to use it. Now to delete everything, we can simply use the delete function, and I will let you go after we delete it. And we deleted the one of the elements, the second element of X, and then it compresses it and reports it back to us. Now, interestingly enough, X and Y, that act of deletion made Y into a new object. So basically what deletion did is it copied it, messed with the copy, and then put it back in the original name. And at that point, it loses equivalence. All right, this seems like a good time to stop. You'll do sorting and stuff in lab in a moment. I'll see you in about 5 to 10 minutes, 7 to be precise. Thank you for your attention and patience and pretending to care.
It's going to be at 5.
I can't download Lab 8.
Can't do what?
It says it can't download securely. Every time I try to download
That's security on your thing. So I will verify that Lab 8 actually exists. I can do that real quick. We thank Texas Tech for that yet again. Let's see, simulate Lab 8, go to Blackboard. Do not make me log in. Lab 8, you said?
Yeah, Lab 8.
It's there. It's your browser issue. You need to figure out. You're gonna have to ask somebody that knows how to do that. Yeah, I feel your pain, but I can't. I don't know how to defeat it. Used to have this on a secured server, and that never worked. So I quit doing that. Do you live on campus or are you in an apartment somewhere? Try to get to a Wi-Fi that's not Texas Tech Wi-Fi, like Starbucks or something. See if you can get to it from there, because that will. I put my coat on backwards.
I got my Blackboard back, so what do you want me to do about the first part of the test?
The guess and check part.
Yeah.
Send me an email. I'll go ahead and open up a test for you. You can just take it.
Okay, and do you want me to like go ahead and turn in all the ones that I didn't turn in through Blackboard to Blackboard?
If it'll let you, do it. If it resists, don't worry about it because I got your emails.
Okay.
But I can't upload to your space. You can. If it's still open, even if it's going to say late, go ahead and do it. That's easier for us to grade.
Okay. Thank you.
Yes, Mark Preto, you were here. We got a big L instead of a 1.
One more question. When did the firm speak to you about auditing? I'm a transfer, so this is my second semester here.
You're assigned to me?
Yes, sir. And I'm having issues with who I was recently speaking with. And we had you CC'd on the email, but it was pretty old.
Later this week would be good.
Okay. I have you tomorrow at 8, so I could always
Okay,
get with you then. So after class.
okay.
You said you used to do concrete canoe stuff.
Yeah.
You're, can I